So we've talked about observing phenomena, then researching the phenomena, and coming up with a prediction or a hypothesis. Now, the next part of the scientific method is to test that hypothesis. And that's collecting quantitative data to support your prediction or your educated guess. In astronomy, we measure and collect quantitative data. And when the scientific method was being developed, before we could measure phenomena in space, we would do qualitative observations or qualitative data on the phase of the moon that we just saw, or on the number of sunspots that we could track, or on the length of day. So, or I'm trying to think of qualitative data that would help you. The moon's a huge one, and the phases of the moon are a huge one. The day of an eclipse, and eclipses would be very dramatic for people thousands of years ago who did not understand and couldn't predict them. So these are qualitative observations, and later as we developed instrumentation, we could add quantitative observations in testing our educated guess, our prediction, our hypothesis. On top of that, there's basically two types of data: retrospective quantitative data, so measurements from the past, and prospective measurements from the future. Now, we've already talked about light years and the fact that light takes so long to move across space. So in general, astronomy deals with retrospective data from the past. We can't really test anything in space prospectively. We can test equipment that goes into space prospectively, but that's not really testing space phenomena. It's testing equipment instead. When we talk about prospective tests, we're talking about experiments. And obviously we can do experiments in physics and in biology and in chemistry. And all of this scientific method evolved from astronomy, the first science. Although some people would say meteorology might have been the first science. I think it's up for debate. From the first sciences, and then moving into the higher sciences of physics, biology, and chemistry that deal with experimentation. In experimentation, you deal with variables. We're going to talk about that. These experiments are designed for reproducing. You are supposed to share your results, and you are supposed to encourage other scientists to reproduce your results. Science is not a competitive sport, and it's a very collaborative effort for mankind. When we talk about variables, these quantitative factors, they are the factors that are impacting cause and effect in an experiment. And I realize that in astronomy we're not working with experimentation, but we are working with the scientific method, so I really want to go into this a bit. Variables are generally the quantitative factors that you use in mathematical calculations, that you use in mathematical modeling, in charting, in tables, in graphs. So that's how we use these variables for analysis. There are different types of variables. There are independent variables that you control and you change in the midst of the experiments. For instance, okay, we can actually do experiments on the solar panels at CCM, and we can be in control, and we can change the number of solar panels that we use, and we can change the dynamics of the solar panels, the characteristics of the solar panels that we use. We can also look into variables the amount of ozone in the stratosphere. That's actually changeable from winter to summer. So we can change the time when we do our experiment to look at measurements that happen as a result of different levels of ozone in the stratosphere at different times. These would be independent variables, variables that we change. They can be individual variables, like they can be the level of ozone in the stratosphere over the South Pole during June, a very, very set variable. Or they can be groups of variables, like types of spacecraft, Falcon Heavy versus Falcon 9, Saturn V versus Gemini. It can be ages of stars, young stars, middle-aged stars, old stars. It can be groups of types of moons, all right? So you can have variables that you control. They can be single variables, they can be groups of variables. Then there are dependent variables. And after you've changed your variables, they impact another variable. For instance, if you looked at the number of solar panels on a space probe, that may determine the distance that that space probe goes over time. So you could control the number of solar panels that you put on a space probe, 2, 4, 6, 8. And then you could predict how far that space probe is going to go based on the energy that it has. And you could run experiments on that. You could look at ozone levels in the fall and in the spring in different areas, and you could predict the skin cancer rates 10 and 20 years later, because the skin cancer rates are the dependent variable on the ozone levels. Conversely, that distance that the space probe goes is a dependent variable based on the independent variable, the number of solar panels on the probe. And then you would, after you look at your variables and you set out the variables that you're looking at, you devise a procedure to test those variables. A procedure to look at how far that space probe is going to go in the universe and how you're going to collect that data. You set down a procedure, a means of gathering data as part of the scientific process. So there is an observation, research, a hypothesis, selection of variables. Then you develop a procedure to test those variables. When you devise that procedure, you have to have a way to record your data that you're collecting. And you're recording the data without analyzing it. You record all the data in charts with no analysis at all. Analysis tends to bias your data. You're thinking about the end before you get done with what you have in your procedure. So your data is collected in a table in a very, very specific way. And the independent variable, for instance, the number of solar panels, generally goes in the column, okay, in the first column. So number of solar panels, 2, 4, 5, 10. It's a way to systematize your tables for the data that you're collecting. All scientists know to look for the independent variables there. Conversely, in the tables that you're collecting, you might look for the dependent variable, the distance that that probe went. So let's say you have 3 probes, okay? For this one probe, I'm 1/3 of the way through my experiment. For 2 solar panels, that probe went 1,400 kilometers. Then for 4 solar panels, that probe went 3,000 kilometers. For 5 solar panels, something happened. The probe only went 2,500 kilometers. Something happened there. But that's okay, because you're going to get a second reading from a second probe and a third reading from a third probe, and you're going to look for outliers in your data. But you can't look for it yet. You can't analyze your data yet. You just have to record your data and and make sure that someone else can reproduce your data collection. Reproducibility is very important to the scientific method. When you finally go and analyze your data, there's another whole set of structures that help scientists to understand what you're looking at for. For instance, when you go and put it into charts, now your independent variable goes on the x-axis. So for instance, the number of solar panels, 2, 4, 6, 8, goes on the x-axis. And then you might have bars in a bar chart, or you might have points. For your dependent data, your distance, 1,400 kilometers, 3,000 kilometers, 2,500 kilometers, are on the y-axis. The dependent data is on there. So these are very structured ways that people can come in and look at your data and try to reproduce it and then analyze it in the same way. So the scientific method lends itself and draws to a close in the conclusion. So does the data and does the analysis support my suggestion, my prediction, my hypothesis? If yes, then you can use your hypothesis to bolster a theory, an explanation on how the phenomena occurred, or even why the phenomena occurred. If the data supports your prediction, your hypothesis. If no, and most of the time it is no, then you have to think, okay, do I need to change my hypothesis? Or do I need to change my method? Or do I need to change my instrumentation? Or do I need to change my analysis? What do I need to do to find evidence that supports the theories and laws that led to my prediction? And that can take time. And for instance, in COVID, people are saying they think that science is black and white. They think there's an answer here and an answer there, and everything else is a conspiracy theory. We will learn in the next chapter. Science takes thousands of years to get it right. You will see how many people, including Newton, got it really wrong. Kepler got it wrong. Copernicus got it wrong. But there's a thread there that people can reproduce and refine and refine and refine. That's what's happening now with COVID. So the scientific method is the key to climate change. The scientific method is the key to COVID. And it's very important for the goal of this course to teach you how to think critically and independently by the scientific method. Talk to you soon.